Here we are going to go through the nucleophilic substitution, elimination and EZ isomers pack of questions. So in question 1, the diagram shows some compounds made from a halogenoalkane. So here's our halogenoalkane in the middle, and there are 3 reactions going off indicated. I'll just draw over those arrows in red so you can see the 3 reaction pathways. Each of them has their own reagent. Reaction 3, they haven't provided a reagent yet, so I might have to think about what that reagent would be at some point in the question. So this is a little diagram that's very similar to diagrams that are very popular in A-level style questions, with 3, 4, even 5 different reactions coming off one central compound. So question A, draw the displayed formula of compound J. Okay, so J is the product of the reaction between the halogenoalkane and aqueous sodium hydroxide. So when we use sodium hydroxide aqueous, the type of reaction we get is a nucleophilic substitution reaction that will replace the Br of the halogenoalkane with an OH. So that's going to be CH3, CH2, CH2, nucleophilic substitution to OH. Crucially, question asks for a displayed formula, so it must show every bond. So let's draw that out now carefully. 1, 2, 3 carbons, then the O, then the H. Let's fill in all the remaining hydrogen atoms as well. Name the mechanism for reaction 2 and give an essential condition used to ensure that the propylamine is the major product, CH3, CH2, CH2, NH2. Let's have a look at reaction 2. Reaction 2 is the reaction of the halogenoalkane with ammonia. So we can see here we have another nucleophilic sub. So reaction 1 is a nucleophilic substitution. Reaction 2 is also a nucleophilic substitution. The ammonia is acting as the nucleophile. So the name of the mechanism then, nucleophilic substitution. And if we want to ensure that as much of it goes to the amine as possible, reducing the possibility of successive substitutions, then we need to use excess ammonia. We need to use more of the ammonia than of the halogenoalkane starting material. Switching that condition around and using an excess of the halogenoalkane would lead to successive substitution, something that we cover a little bit more in the amines topic of year 13. Have a calculation. Let's calculate the mass in grams of propylamine produced from 25.2 grams of the bromopropane, the 1-bromopropane in reaction 2, assuming a 75% yield. Okay, so the reaction proceeds as at a 1-to-1 ratio, so 1 mole of propylamine can be formed from 1 bromopropane. So it's 1-to-1. So we need to work out first of all how many moles of the 1 bromopropane we have. So we've got 25.2 grams of 1 bromopropane. So that is 25.2 divided by the MR. So we add 3 carbons plus we've got 3, 4, 5, 6, 7 hydrogens and a bromine atom. We get 122.9. So that is equal to 0.205. So that's the number of moles of the CH3CH2 CH2Br is 0.205. Okay, so it would be 1 to 1. So if we had 100% conversion, then the number of moles of the propylamine that you'd expect to get, if we had 100% conversion, would be 0.205. However, we've only got a 75% yield, so the number of moles we've actually made multiplied by 0.75, and that is equal to 0.154 moles. So the mass is equal to the 0.154, the number of moles, times by the MR of propylamine. So that's 1 nitrogen plus 3 carbons plus 3, 4, 5, 6, 7, 8, 9 hydrogens. So that is equal to 59. So 0.154 times by 59. And the answer is equal to 9.07. Always worth checking back for a calculation to see whether the question mentions the number of significant figures, or to always try and give it to an appropriate number. So look at the numbers in the question. This mass has been given to 3 significant figures. This percentage has been given to 3 significant figures. So our answer should also be to 3 significant figures. Okay, when reaction 2 is carried out under different conditions, a compound of molecular formula C9H21N is produced. Draw the skeletal formula of the compound. Now this is a question that doesn't really come up until you've done the amines topic in year 13. It's to do with successive substitution. So instead of making the primary amine, as we have done in the earlier part of the question, if we use an excess of the halogenoalkane, then the amine produced can act as a nucleophile and react successively with each time it reacts with a different molecule of the halogenoalkane. Okay, so for example, I'll just show you one substitution so you can get an idea of what this is like. So we've got the halogenoalkane. I'll do it as a skeletal formula because that's what the question's asking for. So we've got our halogenoalkane, and in the second step, instead of another molecule of ammonia doing a nucleophilic substitution here, what we can actually have is we can have the halogenoalkane reacting with another molecule of the amine product. I'm just going to do this as a skeletal formula as well. Okay. Oh, I did a funny thing. That's better. Okay. So what we can have is this happening, and that would produce and do this. And then that secondary amine could react with another molecule of the halogenoalkane starting material. So I'll draw that here. And so the final skeletal formula would look like this for the tri-substituted. So we've got C9H21N. So you hopefully can see that there are 9 carbon atoms bonded to this nitrogen. This is now a tertiary amine. And so this is the final answer. You didn't need to do all of the mechanism that I've drawn out there. I just wanted you to understand where that came from. So it's where the product of the reaction is acting as the nucleophile for the successive substitution. And so that's where you get to that final product. So that's something that we do cover in the amines topic in year 13. So the functional group here is a tertiary amine. The classification is tertiary, and the functional group part is the amine. And just bear in mind that's something that comes up in year 13. So the next part is to identify the reagents and conditions used in reaction 3. So we need to go back and remind ourselves what's happening in reaction 3. So in reaction 3, our halogenoalkane is being converted into an alkene. And so that reaction is called an elimination reaction. Let's come back down here. So the elimination reaction requires us to use sodium hydroxide or potassium hydroxide. And that must be in ethanolic conditions. And it must be hot. Okay. Name and outline a mechanism. So a mechanism for reaction 3, it's elimination. Here we have our halogenoalkane. And what's going to happen here is that we're going to need to draw hydrogen on there. Our hydroxide is going to act as a base in these conditions rather than as a nucleophile. So instead of doing nucleophilic substitution, our hydroxide ion is going to accept a proton, acting as a base. The proton is then going to give up its electrons to form the double bond, which causes the leaving group, the bromide ion, to leave. And so our product is propene and a bromide ion. So just running back through that question so you can see where the marks come from in a question like this. So the displayed formula, obviously there's 1 mark for that. In the next part, the name of the mechanism and the condition both gain a mark each. In the calculation we've got 3 marks, so 1 for working out the number of moles of the halogenoalkane, 1 for the amine using the percentage yield, and then 1 for converting that back into the mass. You can only get the mass mark, however, if you've given it to an appropriate number of significant figures, for 3 marks there. The skeletal formula of the compound, so the only thing that's going to get you any marks here is that skeletal formula, but sometimes on a different scrap of paper, if you're not sure of the product of an organic reaction, it can be really useful just to draw out the mechanism. The functional group is an amine, and the classification is a tertiary amine. So we've got 1 mark for the structure, 1 mark for the classification. Reagents and conditions, sodium hydroxide dissolved in ethanol and hot will get you a mark for the conditions, 1 mark for elimination mechanism, and then a mark for each correct arrow. This one, and this one gets you up to 4 marks. Question 2. 2-bromo 2-methylpentane is heated with potassium hydroxide dissolved in ethanol. 2 structural isomers are formed. State the meaning of the term structural isomers. Okay, so this is where we have to give the meaning of the term, so we have to give a standard definition. Okay, so a structural isomer is a compound with the same molecular formula but a different structural formula. So that's the official definition. What it means in practice is compounds made up of the same number and type of atoms but bonded together in a different order, in a different way. So that could give rise to different structures in terms of the skeleton of the molecule, so different branches, straight chains versus branch chains, different positions of the functional groups, or it could include different functional groups altogether. So those are the different types of structural isomerism. Name and draw the mechanism for the formation of one of the isomers. So we've got 2-bromo, 2-methylpentane, heated with potassium hydroxide, dissolved in ethanol. So let's start by drawing our skeleton. 1, 2, 3, 4, 5. Hang on a minute, I've drawn 6. 1, 2, 3, 4, 5. We've got 2-bromo, 2-methylpentane. And we're going to heat it with potassium hydroxide dissolved in ethanol, so it's going to do an elimination reaction. And so we can take hydrogens from either side of the carbon attached to the bromine. So I'm going to do the elimination from this. It doesn't matter which one, it's just one of the isomers. First step then is the attack by hydroxide acting as a base, and the formation of the double bond, and finally the bromide ion leaving group. There we have one of our isomers. You might have drawn a different isomer there. You might have drawn, we've got E and Z, so you might have drawn the E isomer, or you might have drawn the Z isomer. And you might also have drawn the lone pair at the end, so you could have drawn have a look. We could have had hydrogen here, that would have given rise to this isomer here. And in fact, we wouldn't have had E or Z because in both situations we've got the same group on the end of the double bond. So in the top example, I'll just show you the blue here, we've got a CH3 and a CH3, they're both the same, so that couldn't be, that couldn't have E or Z. And then this one has a H here and a H here, so that couldn't have E or Z either. So we've just got two two isomers possible here, one with the double bond on the end, carbon number 1, and one with it on carbon number 2. Question 3. Two reactions of 2-bromopentane are shown. The C5H10 formed in reaction 1 exists as a mixture of 3 isomers, one of which is pent-1-ene. 2 of the isomers are a pair of stereoisomers, so this must be E and Z, because C5H10 is the formula for an alkene. All 3 isomers decolorise bromine, so that's also telling us that they must all be alkenes. The same reagent is used in both reactions. The product is determined by the choice of conditions. State the reagent and conditions for each of reaction 1 and reaction 2. So if we'll have a look at reaction 1, we've got an elimination reaction. We're going from a halogenoalkane to an alkene. So this is elimination. And so we need sodium hydroxide in ethanol. And in the second example, we've got nucleophilic substitution. And we've got, this time, our sodium hydroxide is aqueous to act as the nucleophile. So let's add this to our answer down here then. So reaction 1 is elimination, and it requires sodium hydroxide dissolved in ethanol and hot. Reaction 2 is nucleophilic substitution. It requires sodium hydroxide, aqueous and warm. And the role of the reagent in each reaction is the next part we've got to do. So in reaction 1, in elimination, the sodium hydroxide is acting as a base. And in reaction 2, the NaOH is acting as a nucleophile. Name and outline the mechanism of reaction 1 for the formation of pent-1-ene. So let's draw out our starting material. And then to make the pent-1-ene, we're going to be putting the double bond on carbon number 1. So we'll need to take the hydrogen from carbon number 1. Our 3 arrows again. And there's our pent-1-ene. Go back to the question, just make sure we've answered all parts of it. Always worth doing. Reagents and conditions for each of reaction 1 and 2. So we've got reaction 1, sodium hydroxide, ethanol. Reaction 2, sodium hydroxide aqueous. Conditions, we've got hot, we've got warm. We've got the role of the reagent as a base and a nucleophile, and we've got the mechanism for the formation of pent-1-ene. Okay, so we've done all the parts of that question. Okay, next part. All three isomers of C5H10 contain the same functional group. Draw the displayed formula of pent-1-ene, that's the first part. Draw the structures of the pair of stereoisomers and give their full IUPAC names. That's the next bit, and explain the origin of the stereoisomerism shown. That's the next part. Okay, so let's draw the displayed formula of pent-1-ene to begin with. 1, 2, 3, 4, 5. And then fill in our hydrogens. So had we taken a carbon atom from the other side of the double bond, the other side of the carbon with the bromine on, we would be here. Okay. And so we would have two potential isomers. We would have this one, and we would have this one. Note how I've drawn the hydrogens on either side of the double bonds on either side to each other. So in the one on the left hand side we've got the two priority groups, the CH2, CH3 and the CH3 are on the same side and the two hydrogens are on the opposite side. So this one is Z pent-2-ene. And in this example here we've got the hydrogens on opposite sides and the priority groups on opposite sides to one another. So we've got the CH3 on the opposite side to the CH2 CH3, and that is therefore E pent-2-ene. And then finally, we mustn't forget the last part of the question, which is to explain the origin of the stereoisomerism formed. And the reason we have this stereoisomerism is there is no free rotation around the carbon-carbon double bond. And that's always the case for an alkene, but there must be two different atoms or groups on each of the carbon-carbon double bond carbons. You need both of those things to be able to have E and Z, because you always have no free rotation around the carbon-carbon double bond. You can never rotate around that. But if you take a look at pent-1-ene up here, you'll see that pent-1-ene can't have E and Z because on one side the carbon is bonded to two of the same thing. So we could just turn that molecule over and it would give the same thing either way up. So it doesn't matter that we can't rotate, we can't get two different stereoisomers for that one. Okay, so in this question we're looking at the rates of hydrolysis. So this is an experiment that we did where you added some halogenoalkanes to some silver nitrate. So let's have a look at the question. The rates of hydrolysis of 2 chloroalkanes can be investigated by adding aqueous silver nitrate to the chloroalkanes. During the hydrolysis reactions, chloride ions are liberated slowly, precipitates of silver chloride are formed. Hopefully you remember that silver chloride, that is a white precipitate. We use this as the test for chloride ions. Outline a method to compare the rate of hydrolysis of 1 chlorobutane with that of 2 chlorobutane. State how the method would ensure a fair test. So the first thing to mention is that 1 chlorobutane has the same MR as 2 chlorobutane. So equal volumes will be equal moles. So that's not always the case. So if you are comparing two different halogenoalkanes that have, for example, different halogens, like chlorobutane, 1 chlorobutane with 1 bromobutane, for example, then equal volumes would not equal the same number of moles because the substances would have different densities. In this case, 1 chlorobutane has the same MR as 2 chlorobutane, so there might be something of a slight difference in density, but more or less they're going to have equal volumes, are going to be equal moles, and certainly equal mass is equal to equal moles. So if we use the same mass or same volume of the halogenoalkane, then we will have the same amount. So you use 5 drops, for example, of each halogenoalkane. Okay, so same number of drops. In addition to that, so that's point number 1. In addition to that, point number 2, we're going to use the same volume and concentration of silver nitrate. So for example, 5 centimetres cubed of 0.1 molar silver nitrate. Okay. The other thing you're going to want to do is you're going to have the same temperature for example, a water bath at 50 degrees C and wait for all solutions to reach this temperature before mixing. Okay, and then finally we're going to have to use a stopwatch or a similar device to record the time taken for the precipitate to appear. So you could use a disappearing cross or a reading on a colorimeter to remove some of the judgment there potentially. And then finally it says to compare the rate of hydrolysis. So what we've measured there is the time taken. So the final thing we would need to say is that rate is proportional to 1 over time. Or you could have said the faster time is equivalent to a higher rate of reaction. So just to recap then, the key points here, that you need to have the equal mass or equal volumes of the halogenoalkane. Because they have the same MR, they're going to have very similar densities, and they're going to have the same mass for the same amount of moles. So you could say, for example, use 5 drops of each of the 2 halogenoalkanes. You also want to use the same volume and concentration of silver nitrate. So for example, you could say 5 centimetres cubed of silver nitrate, and you want the same concentration, so you could suggest a concentration. It's enough to say the same volume and concentration, but I always like to give a suggestion in the experiment, so that's why I've given 5 centimetres cubed and 0.1 molar. You also need to make sure you're doing this experiment at the same temperature, because rate of reaction is significantly affected by the temperature. So we need to make sure that both of these are taking place at the same temperature. So ideally you'd put them in the same water bath, set to the same temperature, and wait for all solutions to reach that temperature before mixing them together. To be able to compare one with the other, you need to use a stopwatch, and you need to record the time taken for the precipitate to appear. To make sure that you make a good judgment of that, you could use a disappearing cross, for example a cross on a white tile, when that disappears, when you can't see through that, or you could use a colorimeter. The rate is proportional to 1 over the time, or the less time, the faster the time, the higher the rate of reaction. You could describe it in words. But you need to do something to link how you would use the time to decide which one had the higher rate. Let's have a look at question 4. Alkenes are useful intermediates in the synthesis of organic compounds. Complete the elimination mechanism by drawing appropriate curly arrows. So I've been told the mechanism is elimination. So elimination means hydroxide acting as a base. I have to look for where the halogenoalkane is. It's here. So we can go for a hydrogen that's either side of that. So it's important that we don't go to the hydrogen that's on the same carbon, which is where some of the common error might be made. We're going to go to this one here, and then that can make the double bond, and then that bromide ion can leave. So you get 3 marks, 1 for each arrow. Draw structures for the E and Z isomers of hex 3-ene. Okay, so structures, so we can draw our structures either skeletally or we can draw them as displayed formula. I tend to, when I'm drawing E and Z isomers, I tend to prefer to draw them like this, just because I think that helps with classifying. So with it being hex 3-ene, it's symmetrical. So we've got on both sides here, we've got C2H5. So we've either got the C2H5s, which have the priority because the carbon has the highest atomic number. So we've either got the C2H5s opposite for the E isomer, or we've got the C2H5s on the same side for the Z isomer. State the meaning of the term stereoisomers. So this is another of your standard definitions. So these are compounds with the same structural formula but a different arrangement in 3D space. So you've got the same number and type of atoms bonded in the same order with the same functional groups, so everything about it is exactly the same except the directions that the bonds are sticking out in, and that's what we mean by the different arrangement in 3D space. So it's really important to learn this definition accurately, as it is with all our definitions. The equation for the first reaction in the conversion of hex 3-ene into hexan 3-ol is shown below. Outline a mechanism for this reaction. So this reaction comes in the alkenes topic, so a little bit ahead of ourselves, but I'm going to write out the mechanism anyway. So we've got the reaction, which is going to be an electrophilic addition reaction. So this is just going ahead a little bit into the next topic, which is alkenes. Don't worry if you couldn't get this one right. I have taken the number of marks off the front for this one, but I thought you might be interested to see what this mechanism looks like. So what we have here is sulfuric acid is going to act as an electrophile. So that's an electron deficient hydrogen here. So this is a delta positive hydrogen and delta negative oxygen. And the electron deficient hydrogen acts as an electrophile which attracts the electrons of the double bond. And this creates an intermediate carbocation. And have a hydrogen here. And then in the second step, we've got our hydrogen sulfate ion, which is then attracted to the carbocation formed in the first step, and that produces the molecule shown in the formula up here. So that is an electrophilic addition reaction. So they come up in the next topic, which is to do with alkenes, the reaction of alkenes. In terms of the marking for this is worth 4 marks. So there's a mark for the arrow from the double bond to the hydrogen of the sulfuric acid, and a mark for the second arrow that goes from the bond between the hydrogen and the oxygen of the sulfuric acid to form the hydrogen sulfate anion. There's a mark for the structure of the intermediate, showing the carbocation and its position. And then finally there is a mark for the arrow going from the hydrogen sulfate anion to the positive charge of the carbocation. Question 5. Nucleophiles react with bromoethane in substitution reactions. This type of reaction is illustrated in the following scheme. So we've got another scheme now where we've got halogenoalkane doing 3 reactions. We've got potassium cyanide in the first one. So sometimes it's useful to get this down straight away, nucleophilic sub. We've then got reaction 2 with ammonia. Ammonia is acting as a nucleophile, so this is also nucleophilic sub. And then in reaction 3, we're going from the halogenoalkane to ethanol, which is also nucleophilic sub. So all 3 of these are nucleophiles in substitution reactions. So what is a nucleophile then? So a nucleophile, another definition, you've got to learn it, which is an electron pair donor. Not just an electron donor, it's got to refer to a pair of electrons. Outline a mechanism for the reaction of potassium cyanide with bromoethane. So cyanide ion going to be attracted to the delta positive carbon atom. That's our nucleophilic substitution reaction. Just worth 2 marks there. So in terms of marking points, we've got 1 for this arrow and 1 for this arrow. Make sure that your compound has the right structural formula before you make a start. If you've got the wrong structural formula, you will get a penalty for one of those arrows. Explain why an excess of ammonia is needed in reaction 2 to produce a high yield of ethylamine. So this is to minimise the chance of further substitution. So it's a further substitution with the product amine acting as a nucleophile and reacting further. If we make sure there's a high excess of ammonia, that is less likely to happen. When potassium hydroxide reacts with bromoethane, ethene can also be formed. So what happens here is an elimination reaction. So we now need to draw our mechanism for elimination. Oh, hang on a minute. I've drawn. I thought something had gone wrong there. Well, propene. We'll just make our alkene. It's just ethene that's been formed there. I made propene. That's better. So in terms of marks there, we've got 1 for saying elimination. And then we've got 1, 2, 3 for each of the arrows. Okay, so let's have a look at the multiple choice questions now. How many different alkenes are formed when 2-bromo-2-methyl butane reacts with ethanolic potassium hydroxide? So always when you're doing questions like this, I would do a little sketch. And we've got 2-bromo-2-methyl. Okay, so we think about where potentially the double bonds could go. So we could make this compound, or we could make this one. And do they have E and Z? Let's have a look. So on either side of this, we've got a H and a H. so that can't do an E and a Z. And either side of this we've got a CH3 and a CH3, so now we've just got 2, so that's A. Okay, so which of these has E and Z isomers? So let's have a look at A to begin with. C2H2Br2. So we could have, this is a molecular formula, so we could put it in this order, and that would mean we have got E and Z. So A definitely can have E and Z isomers. C2H3Br, let's satisfy ourselves. This one cannot, because once we've got hydrogens in 3 positions, then that one can't have different molecules. The next one isn't an alkene because it's got 6 bonds to the 2 carbons, so that must be a halogenoalkane. And the next one is also a halogenoalkane because it has 6 substituents bonded to the 2 carbons, in whatever order we do those in. They're both alkanes, so it must be A. 8. Which alkene shows EZ isomerism? So again, it's just a case of drawing them out. We've got 2,3-dimethyl-but-2-ene. So let's draw it out to begin with. But-2-ene. We've got 2,3-dimethyl. So immediately we can see that they've got the same thing on both sides. So that one's going to be, can't have EZ. 4-methyl-pent-2-ene. Have a look at that one. Yep, that's got different. Let's put the hydrogens in so we can see for certain. That can definitely come in E and Z. I've drawn the E form, so that one definitely can. Methylpropene. So here we've got the same thing on both sides. Hydrogens there and methyl groups on the other side, so that one can't. And pent-1-ene, so we've got hydrogens, so they're the same, they're the same, they're the same, but in this one these 2 are different and these 2 are different, so we've got B as our correct answer. And then our final question, Z-retinal, shown in the diagram, is a component in vitamin A. Which of the double bonds labelled A, B, C or D is responsible for the letter Z? So we have to look at each of the double bonds and work out whether it is E or Z. So it sometimes helps to draw your hydrogens in. So we'll look at both sides of A. On both sides of A, the first atom that we get to other than a hydrogen, so that has priority where I've drawn the dot, and this one has priority. They are on opposite sides, so A is E. Have a look at B now. I'll go for a different colour for B. On one side, let's draw our line. We've got carbon and a carbon. That's bonded to another carbon. So the priority, this one's a hydrogen here. So the priority is this one, and the priority on this side when we're comparing the hydrogen with that carbon. So I've drawn my dots here for the priority. So B is also E. Let's have a look at the next one then. Let's have a look at C. So C, we've got a CH3 at the top, and we've got a CH followed by another C. So that one has priority, the green one has priority there. And then at the other side we've got a hydrogen, or we've got a carbon. So now we've got these two are on the same side, so C is Z. And then finally, just to prove that, I'll do this last one in yellow, we've got D. So from D we've got this is priority here. And then we've also got hydrogen here. Oh, hang on a minute, no, that's not priority. My mistake. This one here is bonded to a carbon that's bonded to another carbon, so that one's priority, and then down here that's a hydrogen, that one's priority as well, so that's another E. Okay, so the one that is Z in amongst all of that is C. So the correct answer is C. Tricky little question. But remember, if you get the same atom when you go to the first one, you have to look at the next one it's bonded to and the next one and so on. So when you've got the longer chain on one side of the carbon atom than on the double bond than the other, you need to look at the next atom along. Okay. And that's the end.